but this is one of the very few talks on quantum algorithms, and most of the people in the audience may not know what a quantum computer is, so I'll try to be broad and don't go into the details of quantum algorithms. So specifically, in the past few years, I've been interested in whether it is possible to obtain something called a quantum advantage for scientific computing problems. Obviously, we haven't made it yet, otherwise you have heard it in the news. That's why there's a question mark in the title. But I do want to mention a few things that I think are necessary conditions for achieving quantum advantage. A little bit like the style we heard from Professor Lafa's talk on Monday. I mean, we don't know what the right thing is, but we do know a few things they are not. So specifically, the first part of the talk is more general, and I will talk about these necessary conditions for quantum advantage for scientific computing problems. And then I'll go to more specific progress recently called the linear combination Hamiltonian simulation that doesn't quite achieve quantum advantage, but it gets maybe a little bit a step closer to that for a class of problems. So allegedly, the field started around the time 1980s when Feynman, in the first conference on physics and computation at MIT in 1981, and he said that if you want to make a simulation of nature, he was referring to quantum antibody problems, you better make it quantum mechanical. It means that you build a quantum device to solve these problems, and it is not easy. 4 decades later, and it has met public attention. Specifically, there is this so-called quantum supremacy experiment. The first one was done by Google in 2019. The theory was proposed in 2018. The problem is called random circuit sampling. And then at the USTC, there's in 2020 called the boson sampling problem. The theory backs to Arison and Akipov in 2011. And what those experiments do is not quite relevant to this talk, because really that is about the definition of quantum supremacy. The concept was raised by John Preskill in 2012. He famously asked, is controlling large-scale quantum devices merely really, really hard, or is it ridiculously hard? So what does it mean? It means that I ask whether we can achieve quantum supremacy, which is the point where quantum computer can do things that classical computers cannot do, regardless of whether those tasks have applications. Okay, so if we first lower the bar and ask whether we can do it, turns out to be not so easy, and the random circuit sampling or boson sampling problems are exactly designed for that task. They're not quite related to any scientific or engineering computation problems that we're familiar with. But we hope we're building quantum computers to do something that is actually useful. And when the point is reached that quantum computer actually does something that is useful, this point is called quantum advantage. Are there examples that quantum computers can possibly achieve quantum advantage? There's a definitive example that was given by Peter Shor nearly 30 years ago, and called the Shor's algorithm. The idea is you're given the promise that you have an integer n that can be factorized as p times q. P, q are prime numbers. And this is called a prime number factorization and is the primary reason for us to believe our bank accounts are safe, so on and so forth. The classical algorithm with the best asymptotic complexity, don't confuse that with the lower bound. It's just the best algorithm we have known, we have developed in the past hundreds, if not thousands of years. And it's this method that scales nearly exponentially with respect to the number of bits, called log n. Not quite exponential. There's a number of bits to the 1/3 and then with the exponential, but it is still definitely super polynomial with respect to the number of bits in the system. Shor shocked the world by developing an algorithm that scales polynomially with respect to the number of bits. And it achieves a super polynomial quantum speedup if we're not too don't care too much about the difference between super polynomial and exponential. We can also refer it to exponential quantum speedup. So the problem has achieved the quantum advantage, at least conceptually, because the input is very clear. The input is a single number. The output is very clear. It's 2 numbers, classical information. The classical algorithm is hard. We just don't know the lower bound, but people have tried really, 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 really hard on this problem. And quantum is easy. Okay, so this will go on. Another example of potential quantum advantage is called quantum dynamics. This is really Feynman's original vision for achieving, for designing quantum computers. That is, you start from some state that can be simple, like a product state, and then you time evolve that, and you will get this final state called the Hamiltonian simulation problem. At this point, this state is still stored in the quantum register, and you couldn't get information out of it. And the idea is you measure some observables called O. So you measure some observable at some time t, for t that is relatively large. It is empirically challenging for classical simulation algorithms. Well, they are for one-dimensional quantum systems. There exist these very efficient algorithms called the density matrix renormalization group or matrix product state, depends on which community, or tensor train, depends on which community it comes from. But even for that, the dynamical version of it, that is, you want to simulate this for a long time t, I think is still open question. People don't quite know how exactly the entanglement entropy grows. And for things beyond 1D, I think both theoretically and empirically, people don't know that much about the behavior of classical algorithms. Quantum computer, on the other hand, doesn't face any obvious difficulties once we can build it, because you have a H that is either geometrically local, 1D or 2D, or 3D, and you start from some simple state. It is believed that it will create entanglement, and the quantum computer can just simulate it, because nature simulates that after you design a proper algorithm, and you just observe that. So it is almost good in the sense that the input is simple, can be simple, the output can be easy, the quantum is by definition, the quantum rounding part is by definition easy, because this is what we're building quantum computer for, and the classical counterpart is empirically challenging. So we still think that this quantum dynamics has a very good chance of achieving quantum advantage. Any questions so far? Okay. Yes. Right. Yeah. Well, at least the people don't know how to do it. Okay. Okay. So in scientific computation, most of the problems are neither like cryptography nor like quantum dynamics. We care a lot about more other problems: solving linear systems equations, solving linear differential equations, can be ordinary, partial, stochastic. Want to solve eigenvalue problems. In many problems, they are nonlinear, but those things are much harder inherently for quantum computers. So a shared feature is that most of these are non-unitary processes. In the past 2 decades, especially in the past 10 years, there have been very exciting and ingenious ideas to shoehorn these non-unitary processes into unitary ones. They're really ingenious. They're not obvious, like you just design something, and there are really a lot of deep mathematics going on there. However, they don't directly answer the question whether you can achieve quantum advantage. So what kind of applications we can do to look for quantum advantages? Roughly speaking, we can divide the problems into high-dimensional problems and low-dimensional problems. The situation is actually quite similar to scientific machine learning that there are a lot of experts in the audience and in this conference. So for high-dimensional problem, the bread and butter thing is quantum antibody problems. Can come from condensed matter physics, quantum chemistry, material science, quantum field theory, and the equations include high-dimensional Schrodinger, Lindblad, Dirac equations, so on and so forth. But if you're not a quantum person, per se, and there are still a lot of other high-dimensional problems, including control theory, including probability, such as Fokker-Planck, and also things in optimization. Everything listed here has been a lot of works in the past decade. People try to work on quantum algorithm, quantum version for these problems. There are also low-dimensional problems, starting from a very large number of molecular dynamics for a very large number of atoms, like Avogadro number of atoms, for example. And you can try to see whether it is possible to speed up some even coupled harmonic oscillators, but designed in a very peculiar way. That was important work from Google last year. But also you can ask whether you can achieve quantum advantage for fluid dynamics, Maxwell's equation, or approximate models for high-dimensional problems. And one of the poster child example is the Kohn-Sham density functional theory, which goes back to here. And for all these kind of applications, when we ask whether it is possible to achieve quantum advantage, we're actually really asking a very simple question. That is, whether it is possible to design things that is quantumly easy and classically hard. What does it mean? It means that the quantum input cost should be low. You should think carefully what kind of information you will need from a classical computer. This is often in the stated in a way that is called a state preparation problem. You shouldn't require a classical computer to prepare a state that is overly complicated. Of course, the idea of overly complicated needs to be very much carefully characterized for each different application. The output cost needs to be low. Many works in the literature is about the ending point is to store a quantum state in the quantum register. But that's not good enough, because at the end of the day, you still need to extract information away from the quantum computer. That can only be done with one way, and there's only one way, that is through merriment. And the quantum running cost should be low, which means the circuit depth, the number of quantum elementary operation shouldn't be large. That is actually, that's most what a quantum algorithm is about. And it is, surprisingly, it's actually often the easy piece in the design of a quantum algorithm. And we should make sure that the classical cost should be relatively high in some sense. And this really says that for a lot of the low-dimensional classical problems, you need to think very carefully where the quantum advantage might come from. It's not good enough to just pick an equation and design a quantum algorithm and say, therefore, quantum advantage. You really have to check all the boxes. Interestingly, since Shor's development of the Shor's algorithm about 3 decades ago, the only algorithm that rigorously checks all the boxes and is pretty much only Shor's algorithm, and maybe one or a few examples related to cryptography. You can think the problem is quite hard, certainly should be considered to be much harder than what people considered 3 decades ago, but also there's a lot of room. Specifically, if you just put what I said before, into a diagram, you can think like they naturally form into a pyramid-like structure. The x-axis is the potential range of scientific applications. The wider, the better. And the y-axis is the existing amount. Existing is important because breakthroughs can happen. So existing amount of evidence for quantum advantage, the higher the better. So cryptography, exemplified by Shor's algorithm, stays on top of this hierarchy because, well, it really checks all the boxes, but the range of applications is relatively narrow, viewed from the scientific sense. And then there's a unitary quantum processes. It is, to some extent, quantum computer is designed to do. It has a wider range of applications. There are tons of dynamics problems in science. And we do believe, strongly believe, that quantum advantage will be achieved in that category. To me, the most interesting thing actually lies in this round 3, that is non-unitary quantum processes, because at least the nominal dimension of their Hilbert space is high, and there's a lot of room for designing interesting quantum algorithms from applied math perspective. I'm an applied mathematician. And specifically, this so-called open quantum dynamics and ground state or state preparation problems, or the thermal state preparation problems, I think there are really a lot of room for further developments. And then there's this round 4, which pretty much includes almost everything you can think of in scientific applications, but it is actually the hardest to argue about the quantum advantage, purely because it is hard to argue about the classical hardness. So you can also consider a more quantitative version of this. In round 1, you check the box, input cost is checked, output cost is check, the running cost is low, and the classical cost is provably expensive. We don't, by provable, we don't actually need to have a classical lower bound because that is very, 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 very hard. Well, all we need to say is the best existing algorithm has some sort of a provable complexity, and that is very high. I think that is widely accepted as a good enough criteria. And there are very few examples that I can check all the 3 boxes, or 4 boxes. Round 2 is still very good. If you can argue that the problem is empirically hard, then we think this is also an excellent application for quantum computers. For round 3, you have these question marks here, partly because of the input problem is not clear. Some of these problems, such as ground state energy estimation, requires you to have a good enough initial state. And how to prepare that initial state is often clear, although there have been recent breakthroughs on understanding this. But there are some complexity theoretic arguments showing that you shouldn't expect to have a generic improvement for this problem. And for round 4, we just pretty much don't know anything. I want to emphasize that all the question marks should not be interpreted as a negative signs. Note that there's no cross anywhere. It just says that we don't know very much. In fact, any update on this table, I would consider as a breakthrough in the field. Okay, so if you want to know more on this generic part, Amazon has a 300-page survey on this last October, and it is now accepted as by the Cambridge University Press as an open access book. And I also, the SIME community is also quite interested in this. They have a series of articles on SIME News recently, and also I contributed 1 article, and please feel free to refer to it if you're interested. So can we actually achieve some sort of quantum advantage that is not cryptography and that is not like quantum dynamics? One thing I think is quite within reach, and that is a so-called early fault-tolerant eigensolver. This is really pioneered by Alexei Kitaev, and who won the Lifetime Achievement Awards here, and many of you might be in the talk. And so he pioneered in the 90s, pretty much co-developed the phase estimation algorithm together with Peter Shor back then. It's a remarkably simple algorithm. It's really a very simple circuit. If you don't understand quantum circuit, don't worry. I won't refer to it too many times. Just says that it just uses 1 extra qubit and for some control. And all you need to do is to be able to do some Hamiltonian simulation. And then you do merriment on this single qubit. So the idea is you repeatedly do this in a carefully designed way. And through this merriment of this single qubit, you will be able to read out a whole lot of information. And that was the so-called Kitaev's algorithm in the literature back in the middle of 90s. But I want to say that this field has received like exploding amount of interest in the past few years. Some of the works are from our group in the past few years, but many other groups have contributed on this. And the whole idea, the key idea, is that you can design eigenvalue solvers that is completely different from classical solvers, like a power method or Arnoldi or some other things. It has nothing to do, has little to do with that. And the best algorithms so far, they are actually obtained via signal processing techniques. And there's a really interesting mathematical problems and algorithms have been developed. And I would also like to highlight like this recent work along a similar line by Jian Ding and Ethan Apley, Roger Zhang, who's a theoretical computer scientist, and myself on Fox recently, and really understanding some of this signal processing aspects. And some of this, the algorithms that we developed earlier, such as the work with Yutong, and has been shown, demonstrated experimentally on quantum devices to be effective. Okay, so this is the first part of the talk, and it's not too technical, and I would like to pause here and ask the audience whether there's any question.
two-dimensional Navier Stokes, then let's say you find an element method, you have 10,000 cells.
Yeah.
Then classical method seems unique cost is about 10,000 every step. Right? Because at least you need to look at each cell and what happens. If you keep asking the same question to quantum computers, is there any chance that the cost goes below 10,000%?
Okay, so the question is whether it is possible to achieve like a quantum advantage for problems like Navier-Stokes, right? So yeah, it's a very good question, and that is primarily the reason why for the round 4 you have all question marks, and really precisely to say there is simply not that much room for you to achieve very big quantum advantage. Furthermore, Navier-Stokes is also notorious because it's a highly nonlinear problem. And all the existing quantum algorithms, there are only very few of them, they either lift each classical degree of freedom into a quantum degree of freedom, which means that, I mean, you won't be able to achieve some sort of exponential or even high polynomial convergence speed up, or you need to linearize the nonlinear dynamics, which often is restricted to certain parameter regimes. So you first need to overcome that problem, the nonlinearity, and then you ask the question you just raised, which is whether it is possible to reduce the, let's say, 10,000 too small, let's say a billion, a trillion number of degrees of freedom, and into a logarithmic number. And I think both are challenging because you are running into the data input-output problem.
So the only quantum computer that factor in this case is you reduce the number of degrees of freedom.
I wouldn't say that because I'm not an expert in round 4, but there are obvious difficulties. Let's put it like that. Yes.
So since there is quantum advantage, so the item value problem.
Very good question. So the AX equals to B, yeah, very surprisingly, the best algorithm with the best means with the best computational cost, asymptotic computational cost with respect to the relevant parameters, which are two. One is condition number, and the other is the precision. So those best scaling algorithms, they're all based on ideas of converting eigenvalue problem, AX equals to B linear system of equations to eigenvalue problems. But the solution, the technique is a little bit different. So indeed, the eigenvalue problem plays a very important role, even for solving AX equals to B. Yes. But not exactly the same technique. Okay, so let me switch gear and talk about this linear combination of a Hamiltonian simulation. The question one asks is how to solve so-called non-Hermitian dynamics. It's not Hermitian or unitary dynamics anymore, with optimal state preparation cost. It doesn't tell you how to prepare an interesting initial state, but it is often the case that the initial state is not so easy to prepare, and we want to reduce the input cost. Okay, so it's a very modest goal. So this is joint work with Dong-An, who was a former grad student at Berkeley working with me, and he later became a Hartree postdoc fellow in Maryland, and he's joining Peking University this year as assistant professor, Professor Andrew Childs from University of Maryland, and also now Professor Jinpeng Liu, who was a former Simon's quantum postdoc working with Umesh Vasarani and myself, and he's now joining Tsinghua University Yao Math Center here as assistant professor this fall. So the problem we consider is actually bread and butter applied math problem, time-dependent linear differential equations. So you want to solve this with AT and starting from some sort of initial state. By having this cat here means that the initial state is without loss of generality normalized. So if AT is AI times a Hermitian matrix, this is called time-dependent Hamiltonian simulation. And there are many good algorithms for that. For general AT, a quantum ODE solver approximately implements this time-ordered matrix exponential, you might not be familiar with the expression. So just think A is time independent, then you're just simulating e to the minus at is just a matrix exponential problem. It has tons of applications, like a lot of classical linear ODEs and PDEs, imaginary time evolution, also scattering problems, non-Hermitian quantum dynamics, something called the skin effects has received a lot of attention in the past few years. Also the quantum optical limit of Lin dynamics, they can all be expressed in this form. Sorry. So you can also generalize this to handle the inhomogeneous case by the so-called Duhamel's principle, and you had if you add an inhomogeneous term there. So the setup is that I consider the Cartesian decomposition of AT. Excuse me. So the Cartesian decomposition is something very simple. That is, for any arbitrary matrix A, you can decompose that into the sum of two Hermitian matrices, L, which is the Hermitian part, and H, which is the anti-Hermitian part. And both of them are Hermitian matrices. You can verify directly, and this dagger here means Hermitian conjugate. We also assume LT is positive semi-definite for stability. I also want to emphasize this is a relatively strong version of stability. For weaker asymptotic stabilities, we actually, the algorithm is not directly applicable. So the linear combination of Hamiltonian simulation formalism, what it does is an interesting idea that expresses non-unitary dynamics, which is on level 3, as a set of Hamiltonian simulation problems. It's almost the best you can imagine, because there's no way you can convert this as a single Hamiltonian simulation problem. But if you can write it as a linear combination of Hamiltonian simulation problems, then this can still be efficiently simulated on quantum computers. So specifically, the theorem is this. If A is the sum of two Hermitian matrices, and then the theorem is this matrix, time-dependent matrix exponential, can be written as the integral of this UKT, where UKT are unitaries solving the so-called Hamiltonian simulation problem, where each unitary UK depends on this parameter K. Okay, so let's see why this can be possible. We consider two trivial limits. One is if A only contains the H part, so L is equal to 0. What do they say? It says that this this UK here, L is 0, is gone. So this is independent of K. Then you have e to the minus IHT, but this is independent of K. We're just saying that you are integrating the Cauchy probability kernel and saying this integral is equal to 1. So obviously this is true. And another regime is that if H is equal to 0, if H is equal to 0, you have e to the minus IKLT, you can apply the so-called spectral mapping theorem. That is, you first diagonalize L, and then you just apply this thing to each eigenvalue of L, which is real. But we know that the Fourier transform of the Cauchy kernel is just e to the minus x absolute value. And we know x is bigger than 0, so you just have e to the minus LT. So both limits, they are trivial. But the interesting thing is this holds even when L and H, they don't commute. And it is one of the very few examples I know of matrix identities that are actually not based on spectral mapping theorem. So the previous works for solving generic linear differential equations, they're actually not obvious from the perspective of applied math. So the first work along this should be Dominic Berry in 2010. And it converts the linear differential equation into a linear system, a very large linear system. I'm going to explain what that is. But the idea is that you convert a differential equation into AX equals to B problem, very large AX equals to B, and then you solve it with a linear differential equation solver. So It's not an obvious method, but for a very long time, it is really the method to solve differential equations. The first work that is very different from that flavor was done by a joint work with Difang and Yutong, and called the time marching method. And also, I would like to highlight that Professor Shi Jin and Liu and Yu and collaborators in the past few years have developed a series of techniques called shorterization, and that one is also quite related to the LCHS, at least the original version I mentioned. It provides an alternative perspective of this linear combination framework. If you're interested, I also would like to refer you to Professor Difang's tutorial talk in IPAM last year, and it contains a lot of pedagogical information. So how does the linear system approach work? It's actually kind of interesting, because what you do is you apply the simplest discretization you can think of, such as forward Euler, and instead of solving the differential equation from one time step to another, you just solve them for all the degrees of freedom altogether. I mean, nobody solves differential equations that way on a classical computer. Surprisingly, this was one of the best methods, one of the first and still one of the best methods for solving differential equations. So we compare with the best version of linear systems, like a state-of-the-art linear system approach called truncated Dyson. Then there are two key parameters. One is the largest norm of A. The other is the norm of the solution, ratio of the solution called Q. So, and another is the simulation time T. So you can see that the truncated Dyson method, it performs quite well with respect to the precision. Here it's a polylogarithmic, but in our LCHS is like a polynomial in 1 over epsilon. However, in terms of the query complexity for the initial state, this initial state has a lot of dependencies, Q, alpha, T, so on and so forth. And our method is only OQ. It means that it uses very few queries to the input state. In fact, this is the optimal state of preparation cost, because you can prove a lower bound. There doesn't exist any quantum algorithm to be below OQ. And, but it is not good enough with respect to the query complexity to the matrix A. So we wonder whether it is possible to improve this. And turns out this is possible. This is done by realizing that the LCHS method is actually not a single scheme. It is a family of methods. It's a family of identities that can all be used to exactly express this matrix exponentials, even when A is not diagonalizable. So specifically, there exists a class of Fk. There are kernels, they're holomorphic functions, and meromorphic functions, and so that this is identity. Why this is possible? Intuitively thinking, you can think that if h is equal to 0, all I need is to make sure at least this scalar identity should be correct. I only specify this should be exactly the same for all x that is non-positive. But along the negative axis, I have a considerable degrees of freedom. So for the kernel I said before, I mean, it is like there's a cusp, which is why the main reason why the query complexity is not good. But I can design other f's so that they become smooth, and then the Fourier representation becomes a lot more efficient. So what are the possible choices? The original choice, although it's not quite obvious, is this. If you plug in z is equal to k, you will find 1 minus ik, 1 plus ik becomes 1 plus k squared. So that's the Cauchy kernel. And the near optimal choice is this weird stuff. So what it does is there's a near exponential decay along the real axis that allows you to truncate much, much earlier compared to the original LCHS that decays like 1 over k squared. That's the key idea. But of course, you need to show that such identities exist. But that's really the main observation of this new work. So we can also prove that the near asymptotic decay is near optimal. Means that we can prove a theorem that says that if this kernel indeed decays exponentially along the real axis, then this is 0. It's very sharp. Okay, so in terms of the complexity, we compare with some of the state-of-the-art method. This is the linear system-based approach. You have this polylogarithmic dependence. We also have the polylogarithmic dependence. Beta can be arbitrarily close to 1. You can see that the two almost matches. It still maintains the OQ dependence on the initial state, so that's optimal. Compared to the time marching method, the time marching has inherently a t-square complexity dependence, and this is linear in t. So this is the first algorithm to achieve optimal state preparation cost and near optimal matrix query complexities with respect to all parameters. So let me maybe now say a few words on the general, what's the idea behind this? So the main theorem is this. Again, given AT, I can always split that into Hermitian and non-Hermitian part. And L is positive semi-definite. Then for a class of kernels, there are specific conditions on the class of kernels that I won't go into today. Then this is identity. The proof is based on a matrix version, a matrix value, the Cauchy integral theorem. It's not the Cauchy integral formula, which is usually used to design identities like this, because how that works is, for example, Nick Trefethen and collaborators has done very extensive amount of work. He used this Cauchy integral formula-based ideas like ingeniously, like in the past 15 years, developed a lot of efficient algorithms. The ideas, they're all based on spectral mapping theorem. You have a matrix A, you first diagonalize it, and then you apply some complex analysis-based formula to the scalar, and then you use the spectral mapping to convert that to the matrix. This is not that. This one, what you do instead is actually the proof is not complicated. You take derivatives on both sides with respect to t. You will find that there is some sort of the two sides almost match, except there is a term like related to like a residual term on the right, and you want to show that term as a matrix vanishes. And what you want to show is very similar to the proof of Jordan's lemma in the undergrad, like a complex analysis, and you draw some contours and show that that vanishes, and which gives you this proof. Okay, the near optimality, the statement is like this. So for a class of kernels, if fz decays exponentially, the same class of kernels, actually slightly even broader, so this is a stronger result. If fz decays exponentially on the real line, which means if I were to improve this 1 plus 1 over beta complexity to 2, as I said, beta can be arbitrarily close to 1, bigger than 1, smaller than 1, arbitrarily close to 1, that's okay. But if I literally want to set this to 2, at least the current proof technique says that this fz must decay exponentially on the real line. Then this is 0. So the implication is that the weird choice I gave you before, there must exist other near optimal choices, but that particular one is near optimal. The proof, one of the key steps is actually something called the fragment-Lindelof principle that generalizes the maximum modulus principle to unbounded domains. Maximum modulus says something about the extremal values of holomorphic functions in the bounded domain, and this one you need to do this for unbounded domains. Specifically, the first step of the proof is to show that if something that decays exponentially on the real line, because of these conditions specified by this class, it will also decay exponentially in the entire lower half plane. So let me see how much time I have. Okay, let me very briefly explain what the ideas I just mentioned. So the left-hand side of this identity, let's consider the time-independent version. The time-dependent version is only slightly more complicated than that. On the left-hand side, I take a derivative, okay, which is this. On the right-hand side, I take a derivative. You'll find it's almost the same thing, except there's this reciprocal. And you want to prove this is 0 for that class of functions f. And the idea is that you use a matrix version of Cauchy's integral theorem, similar to the proof of Jordan's lemma, by drawing a contour like on the right half of the complex plane. The second part, the so-called fragment-Lindelof principle, is a little bit technical. And what it says is if you have a function g that is analytic in the lower half plane, continuous including the real line, and is bounded, then, and if you can show that it somewhat only grows exponentially, then it must be bounded. So this is called a fragment-Lindelof. This is the one version of fragment-Lindelof principle. What you do is to move this exponential to here. I mean, you can just multiply g by, divide by g by exponential and then multiply it back. That allows you to establish the first step of the proof, but also the most important step, which is exponential decay on the real axis implies exponential decay on the lower half plane. Okay, so let me conclude. So for, any is correct. So for a class of linear non-unitary dynamics, you can express this as a linear combination of Hamiltonian simulation problems. It, to our knowledge, drastically simplifies, both conceptually and from an implementation perspective, the process of solving this non-Hermitian dynamics. We hope that you can, I mean, the L is bigger than 0. I mean, that type of stability conditions a little bit too strong, and we hope some improvements can be made there, and that'll be quite nice. And it has also has some implications on the complexity improvement for time-independent problems and Gibbs state preparation. So some further ideas like include a better kernel, but as I said, I think the biggest question, one is to generalize whether this can be used for more general eigenvalue transformations. So one thing that is a work in progress with Dong'an, Andrew Childs, and Lexing In is a class of eigenvalue transformations called quantum Laplace eigenvalue transformation. It says that for a class of matrix functions that can be expressed as a Laplace transform of something, then you actually can again use this LCHS formula to obtain meaningful improvements for eigenvalue transformations. And restricted to differential equations per se, I think this weaker version of the stability condition would be the biggest open question. More broadly, as I said, the talk is about quantum advantage for scientific computing problem, not a specific differential equation. I personally think that it is likely to achieve quantum advantage in level 1 once we have a good quantum computer, which is cryptography, and level 2, that is unitary quantum dynamics. But I think that there's a lot more room to develop and discover new quantum algorithms at level 3, non-unitary quantum, I give you an example, and level 4, that is classical, which is something I know very little about. Yeah, there's some co-design perspective. I guess that's not for this audience. So there's actually, I want to say, end the talk with this. So in April, I was asked to participate in this RPI, Ressler Polytechnic Institute, and give a talk there. So they installed the first like a commercial quantum computer like on the university campus, and actually it was also RPI's 200-year celebration, and they decided to install a quantum computer in their university chapel, which is about a century old. Right, so very nice contrast between the old traditional and new technologies. So there were also like a podcast thing associated with that. It was my first time to show up on a podcast, a new quantum era. And the host asked me a question that caught me a little bit off guard. He asked me, is it fair to say that there hasn't been much progress in quantum algorithms since Shor? So I paused for a second, because I froze for a second because I don't know how to reply. I mean, what do you mean? I mean, to me, there are tons of progress. I mean, what do you mean there's no progress? But after freezing for a little bit, I realized that indeed, Shor's algorithm is still essentially the only level 1 algorithm application that is worth advertising to the public, saying, hey, there's some definitive thing that is going. All the others, they are like soft in one way or another and follow a continuous spectrum. But what does it mean? I think it really means that the quantum community might need to find better ways to communicate with the public on what has been achieved. I think there definitely has been a lot of progress since Shor. They are very, very exciting. I think hopefully a lot more mathematicians will get interested in this and contribute to the field. But also, I think it is equally important to communicate on what are achievable. So one should distinguish between a quantum computer on one hand and a wishing well on the other. With this, I'd like to thank you very much for your attention.
Thank you for the beautiful talk. Any questions?
First question is how the condition number of A comes into the picture. I guess that's related to the exponential decay of the things.
The condition number?
Yeah,
for solving differential equations?
Yes.
Sorry, maybe I didn't explain the parameters very carefully. So there's actually no condition number here. So the norm of A naturally extends because you can think like if the norm is too large, then either the dynamics oscillates very rapidly, or you can just rescale the time, right? It is intuitively correct and can be made rigorous that the cost should increase often in the worst case linearly in t. So that's why this one comes in. This one is related to the merriment cost. So you can indeed solve a thing like in the quantum computer, but if the norm of the solution, it is strongly dissipative, for large t, the norm of the solution will become exponentially small, right? I mean, in the worst case, then you need to repeatedly run the quantum algorithm and hopefully get a successful result, which gives you a normalized state with respect to a correct normalized state of the output. So that one will increase the cost, which is why there's this.
So, but in classical way, the condition number basically is saying you'll have a stiff system. You have to take out very fast transition, slow transition. So in here, there's no such a.
Okay. Yeah, that's a great question. So these are, if you were to use like a forward Euler or this kind of methods, you do have such a kind of constraints. In fact, the truncated Dyson is very, very different from classical algorithms that we implement, like a Runge-Kutta or something. It is actually expansion. Okay, maybe let me answer in two ways. One is, for example, this truncated Dyson. You do a high order time-dependent Dyson expansion, literally implement that, like on the quantum computer through a technique called linear combination unitaries. So that is already in the very different regime compared to the classical algorithm. And the two, which is very interesting from applied math perspective, is that quantum computer, other than handling exponentially large degree of freedom, it is also very good at handling high oscillation. The reason is that you can put a very large number of discretization points along the time domain, and many quantum algorithms can be designed and do a quadrature. And many quantum algorithms can be designed to convincingly scale logarithmically with respect to the time discretization points. I'm not saying logarithmic dependence on the final time. That's a physical number. But if you consider the numerical thing, which is the number of time discretization points, I think it is reasonable to argue about the logarithmic dependence there. So that's indeed a distinct advantage that is available for quantum algorithms, and I don't see obvious classical counterparts.
But oscillations could give you trouble in time, this margin.
No. So the stiffness is really about the time resolution. As I said, you actually can afford to put a very fine discretization on the time domain. And that one doesn't only increases the computational cost polylogarithmically.
Then the second question related to this. So if we solve this e to the ik, say h or l, these things, with large k, you have very oscillatory behavior in the space. That's typically hard for classical method.
Right, right.
So quantum computing does not feel this difficult?
It does. That's an excellent question. That's precisely why you have the cost 1 plus 1 over beta. And this 1 over beta is because the kernel decays nearly exponentially, which means that the largest frequency k is log 1 over epsilon to the power 1 over beta. So you multiply it. That's already been factored in. Yeah, that's precisely where that comes from.
So then you exponential decay in the
you truncate the, so you have an infinite integral. You throw out the tail, which is possible because it decays super polynomially. And then the largest frequency is O log 1 over epsilon 1 over beta. You multiply.
Can we say that if we know how to handle the nonlinear dynamics, then most problems in class 4 will be solved? Can we say that?
I highly doubt that there would ever exist a universal recipe to handle nonlinear problems on quantum computers. It's just so intrinsically linear. So as a matter of fact, I'm so far not yet convinced we actually want to use a quantum computer to solve nonlinear dynamics. Because think about where does nonlinearity come from? A very big source of nonlinearity is when you use a nonlinear ansatz to form an approximate solution to a high-dimensional linear problem, right? So my personal take would be to directly tackle that high-dimensional linear problem. But of course, this is just some philosophical thinking. But
so the solution would be raise the dimension of nonlinear problems and to linearize them.
But that's indeed called the Kuhlmann von Neumann linearization. There exists a generic recipe to do that. You can do it. It's a sound algorithm. The problem is that you won't, if the goal is to solve that approximate low-dimensional nonlinear dynamics, it's very hard for me to imagine how you can ever get exponential, even high polynomial converge, like a quantum advantage, not to mention exponential quantum advantage. Yeah, so it's already happening. So just to give a very simple example, I think there are a lot of people interested in this. The quantum field is enormously large. Of course, there's the variational quantum algorithm that you might be familiar with, and a lot of people are working on it. But even in the fault-tolerant regime, there is an exploding amount of interest in quantum error corrections, in the past few years. And for example, Mikhail Lukin's group made this a breakthrough, in last December on this fault-tolerant qubits. But if you want to run fault-tolerant algorithms and for any scientific computing problems, you will at least need to have some sort of continuous gate rotations, more complicated unitaries than just Clifford and T. So is it the best way to do is to use a Solovay-Kitaev and decompose everything into Clifford plus T and do error corrections on each T? It's just unclear. That's just obvious, I think, co-design question. I think there got to be better, more practical answers to this question in the next few years.
So is it possible that the quantum algorithm will be useful before fault tolerance?
I think so. So there are at least two camps. One thinks that fault tolerance happens in a cliff way. We either are in near term and very hard, quickly transition to full fault tolerance. I have natural skepticism of that just by continuity argument. I don't think that is how things usually happen. So I think more naturally it would be we are going to enter early fault tolerant era. You can maybe say that we have entered that since last December, although that's very, very early. But in the next few years, I think it is conceivable that the field enters early fault-tolerant area, and people found ingenious usages of this kind of machines. I think that's a very conceivable thing.
Could we revise the non-unitary dynamics to be unitary, like maybe incorporating the environment as a part of system and just solve the Lin Lin equation? I'm not sure if these two concepts are related, as I'm not
these are extremely related. It's a very good question. They are mathematically speaking, most of the quantum algorithms for non-unitary things can be characterized, incorporated into one of the two categories. One is, at the end of the day, you can only handle a very large unitary matrix. That's for sure. The question is, what do you do with that unitary matrix so that it does the thing you want? So one possibility is to get a corner of the unitary matrix, right? So you have a large unitary, you get a corner of that, and that can be non-unitary, and actually can be used to represent any non-unitary matrices up to a normalization factor. That is called block encoding. That is what LCHS does, secretly. So it actually constructs a big unitary, a corner of that is what you want. The second part, which is the Lin Lin, you said, I think there's, again, an exploding amount of interest. Really, it's a very large field in the past few years on this. And the special property of Lin Lin is that the propagator, e to the LT, is completely positive and trace preserving. It's called a quantum channel. So that gives you the possibility of having a second way of using a large unitary, which is to take a partial trace. You not only take a corner, you take a lot of block diagonals, add them together. And that approach has the advantage that it doesn't lose success probability, and I think people are very actively exploring these ideas right now.
Thank you.
Hi. Have you heard of any quantum advantage for categorification problem?
Sorry, for
categorification problem.
Sorry, I still haven't. Classification problem.
That's
That's like a class 4, right? So the
categorification.
Categorization. Can you give me an example?
Yes, in some sense, you have a huge overdeterminated polynomial system, very sparse, and the goal is to find small subsystem, a sequence of small subsystems to solve the big system.
Have I? And the answer is clearly no. As a field, I actually don't know enough to answer that question.
Thanks for the excellent presentation. So this question may not be that relevant, but as we have discussed, we are trying to solve like AX equals to 0 or AX equals to B for like a quasi-static mechanical system. And so we encountered the problem by using IBM VQE, variational quantum address over that. For example, if you have A and B, which are both scalars, exponential A plus B, just the exponential A times exponential B, right? So in our case, we have exponential matrix A plus matrix B, and we are trying to like express that maybe approximately or asymptotically in terms of exponential matrix A and sequential, because each one of the matrix exponential can be represented by a quantum gate.
Right.
So I'm wondering if there are any fundamentally mathematical approximations or.
Yeah. So I think this answer can go down a couple of different directions and gets a little bit technical. I'm happy to answer questions after.
Okay. Sure. Yeah.
Quick question is alpha and beta related to the error, and the number of time interpolation related to the error?
Sorry, which?
That's quantum algorithm. I suppose if you run the simulation long enough, there should be an error, right?
Right. That's the
procedure. Alpha and beta and t, the time discretization related to error. How?
Oh yeah, you factor them in, and so far you assume they're independent parameters, but in the end, you do construct a solution with a trace distance epsilon and to the.
So this complexity is compared
right.
under same error.
This is the yeah.
Oh, okay. Oh, I see.
Trace distance.
So the question, let's speak again.